Good evening, everyone. Welcome everyone. Welcome to the faculty and members, friends of the Institute, to this widely anticipated talk. And I have the honor of introducing Robbert Dijkgraaf, who is, of course, the director and the Levy professor here at the Institute. It's also a great pleasure to see Peter and Helen Goddard in the audience here and to have you remain as members of our community. So Peter, Helen, thank you very much for coming this evening. As many of you know, I am not a physicist, I'm not a mathematician, I'm not even a scientist. It seems hardly appropriate, therefore, for me to comment on Robbert's distinguished scholarly career that explores the relationship between mathematics and particle physics. However, I did serve in the search committee that recommended Robbert to the trustees, and I was privy in this connection to what scientists around the world had to say about Robbert's career and his scholarship, and they were uniformly and infectiously enthusiastic about the work he had done as a scientist. And this, of course, was central to our excitement in recommending him to the Board of Trustees. However, I can talk more knowledgeably, perhaps, about Robbert as a public citizen of both science and a broad range of additional cultural concerns. By public citizen, I mean someone whose concerns, empathy, and interests reach well beyond his own scientific work. As president of the Royal Netherlands Academy of Arts and Sciences and co-chair of the Inter-Academy Council, Robbert has demonstrated his great capacity not only as an ambassador for science, which really comes natural to many scientists to be an ambassador for your profession, but to be an ambassador from science to the broader community. This is, I think, very essential, very important, and much rarer indeed. His broad interests and accomplishments in science education and in bringing significant relationships between science and society are really quite extraordinary, and all these accomplishments have been widely recognized by a series of distinguished awards. I was fortunate enough to work with Robbert on a project for the United Nations, and I could not have been more excited when it became clear to the search committee that we might be able to attract Robbert and his family to this community. Robbert, we are delighted to have you and your family in this community, and we look forward to your remarks, which are entitled The Frontiers and Limits of Science. Ladies and gentlemen, Robbert Dijkgraaf.
Thank you, Harold, and thank you, ladies and gentlemen, for appearing here. I must say, I'm a little bit nervous to have some of the members of the search committee in the audience, and I hope you kept a receipt. It's a delight to talk about perhaps the few more general aspects of, I would say, kind of academic life. And coming from the Netherlands, I feel very privileged to be here, and of course also speak the international language of academic world, which is English. But in fact, I really hate the fact that the wonderful word which is wetenschap in Dutch or Wissenschaft in German is very difficult to translate because we have always say arts and sciences or humanities and sciences. So if I talk today about sciences, I actually feel I'm talking about all academic ways to acquire knowledge. And I want to talk to you about the frontiers, but I guess also between the borders between the various fields, and in the end about the limits. And also frontiers within science, and also frontiers between science and the rest of the world and the community. I want to start with this kind of, I always found very wonderful quote by Arthur Wellesley. That's of course the Iron Duke who conquered Napoleon, and I hope you all know why he was called the Iron Duke, because when he finally became Prime Minister, he was so unpopular that he had to reinforce his house with iron gates to keep the people out. But he said at the end, so there's this wonderful quote, that in business of war, and in fact all of life, what you have to do is to guess what's on the other side of the hill. And history has it that when he was retired in his country estate, he would take friends in a little stagecoach, went into the hills, and they would play this game. They would look and guessed what was on the other side of the hill. Is there a forest? Is there a lake? Is there a village? And apparently he was very successful in doing so. So I think he had something what I would like to call tunnel vision, but then in a positive sense. I think the thing that we are looking in visionary scholars to see in some sense things that other people cannot see. And I think this is what happens if you go through the tunnel. I think this is this kind of heroic portrait of a scientist, in this case William Herschel, of course famous because of basically the first person to see a new planet, Uranus in his case. As you know, born in Germany, a wonderful oboist, composer of more than 30 symphonies, and then finally at a later stage of his career decided that he could also have a life in science. And this is one of these famous discoveries. This is the discovery portrait of an invisible phenomena, namely infrared light. And so what Herschel did, he measured the light, which was already a wonderful idea, to measure the temperature of blue light. Then he measured the temperature of red light, was hotter, and then he put his thermometer here next to the rainbow and found that it was even hotter. And so a wonderful discovery, something that nobody has seen before, namely infrared light. Now, I think it's a beautiful metaphor of what science can do, because in some sense this little piece of what we now call the electromagnetic spectrum that we see extends all the way out to radio waves on one side, to very high energy gamma rays and X-rays that, for instance, our astronomers use. And that's actually the person who kind of unified this. Maxwell was actually a great hero of Abraham Flexner, the founding director of this institute, but in fact also of Einstein. In fact, these two portraits are here at the institute, and of Maxwell and Faraday, and they would hang in Einstein's office. So I think in some sense a great example of unification in theory. And now it means that this is not the institute pond, but it could easily have been. No, there are amateur infrared photographers, and they look through their cameras into the world through infrared light. So they opened up really a whole new possibility. And of course you can do it in a more professional way. This is what astronomers do. These are pictures of the Milky Way, not only use the optical one. This is what you see if you look at the night sky. But all these other images you can see once you use sophisticated machines, telescopes, satellites, to view the universe and all these different kinds of light. And of course you can discover great things. And one of the greatest discoveries, I think you probably have heard many talks about this, is when you look at the sky using microwaves. And if you look at the sky using microwaves, you get this beautiful pointillistic painting, which is in some sense the baby photo of the universe. It's one of the icons of modern astronomy and cosmology. It's a picture of the universe when it was just born, 400,000 years after the Big Bang. And perhaps you've also seen that it's actually a painting that has a signature on it. It's signed, because you can here see the initials SH of Stephen Hawking. And in fact, you can find a website where you can actually indicate everything that you see your initials here too. And it's like the modern version of looking at the clouds and seeing all kind of imaginative figures. But why I want to show this picture is that it was again one of these moments where we saw something which was basically invisible, because using this and other data, cosmologists the last 10 years have in a sense weighed the universe, and they have found that if you weigh the universe, that a large fraction of the universe is essentially unknown. That is, we do know there is something, there is matter, there is other forms of energy, but if you take the known amount of matter, gases, radiation, everything that's known to present-day astrophysicists, it only adds up to 4% of the universe. So I often say that astrophysicists are extremely lucky that they know exactly what they don't know, namely 96%. And often then I ask other colleagues, what's your percentage of dark matter? What do you know that you don't know? And I often feel this is perhaps a good image. In the old days, when people were making charts, mapping the world, where still large parts of the world were unmapped, the poor map makers, they've had great difficulty just leaving empty space. So they put all these great sea monsters there, which, of course, one by one disappeared. And often I feel like a scientist, perhaps like the people here in this little boat, navigating this sea of sea monsters and in some sense exploring things that we know we don't know. I would like to call it dark knowledge, and there are endless amount of examples. And if you think about 4% that you know is actually quite a reasonable number. For instance, if you study Greek tragedies, roughly, I think, 3-4%, less than 5% of the great works is known. Somebody might find them at some point, but we don't know them. If you ask biologists, what fraction of life on Earth, like animals, will have left a fossil, only one, so that you can reconstruct the big tree of life, then a very optimistic estimate says it might be 1%. So we have to deal with these 99% kind of dark knowledge. And give a much more mundane example from Dutch language. The Dutch word for bike, fiets, appeared in 1870, and nobody yet knows where it came from. So this is what my colleagues in the humanities tell me to keep me with my feet down to earth. You might study the cosmology, but think about the origin of everyday words. So, and again, these are just the things that we study which are kind of the known unknowns. There was also the famous unknown unknowns. Perhaps you remember this rather infamous part of a press conference that Donald Rumsfeld held. I think it was a very philosophical remark. That was, of course, on the basis of the invasion of Iraq, and I think it wasn't really appreciated that there are these kind of three kinds of knowledge. But I want to mention this because, again, it's something that we have to be reminded of as scientists every day, that science is, by definition, based on skepticism. This is a famous definition of organized skepticism. And I also very much like this quote of Francis Crick, one of the co-inventors of the structure of DNA, that, oops, what happened here? Oops, it wants to go home. That any theory that can account for all the facts is wrong. Oh, let me just flip this off. Any theory that accounts for all the facts is wrong because some of the facts are always wrong. And this is something that we have to continuously remind you. And I want to give you an everyday example that I liked very much. This is something that perhaps some of you read in newspapers. It appeared almost 2 years ago. There was a British woman, here she's mentioned, who was making breakfast, and she cracked an egg. And she cracked the egg and turned out to have 2 yolks. Then she took a second egg, it cracked it, 2 yolks. The third egg, 2 yolks. At that time, her husband was in the kitchen. The fourth one, they started to make pictures. And when they had 6 double yolks, they phoned the newspaper, because this was a tremendous event. And everybody could tell you the chance of an egg to have 2 yolks is roughly 1 in 1,000. So if this happens 6 times in a row, it's a chance in 1 in 10 to the 18th, which means that you take an ordinary coin, throw it 60 times, and it 60 times lands on tail. So what is the probability that this could happen? And then there was a very interesting debate in the British newspapers about this. A lot of kind of chicken and egg professors were involved in it. And I like the arguments, like these eggs were selected on size. Perhaps the chicken was fed hormones, or they were all coming from the same chicken. And then one of the experts actually one day was in the supermarket, and he saw there a number of boxes that said double yolk eggs. I think it's a good example that we have to remind ourselves that we always have to be skeptical. Now, I want to say something about this process, going back to the Iron Duke, so to say, Wellington, of looking at the other side of the hill. And when I went to my high school in Rotterdam, I always passed this really gigantic statue, which is a statue celebrating a Dutch chemist, Van het Hoff, who actually won the first Nobel Prize in chemistry in 1901. So that time, the Dutch had 100% of all Nobel Prizes in chemistry. And in fact, one of his main achievements was realizing that molecules are three-dimensional. You might think this is a very elementary fact, but at these days, people would write chemical formulas on paper. He writes, no, the three-dimensional shape matters. And in fact, this is in the university library in Amsterdam. These are the little toy models, the little paper models, by which you illustrated the fact that if you have a typical molecule, and you hold it, say, in the mirror, the molecule you get, the mirror image will not be the same. And will have completely different chemical properties, interacting with other molecules. And in fact, this is still, of course, a great theme in modern chemistry. In fact, DNA is, of course, the prime example of this. People don't realize, in fact, there's a website completely devoted to the wrong images of DNA. So it's left-handed DNA. Your DNA, all our DNA in all living material is right-handed. But even including famous biology books, I think just the graphic illustrator decided that it looks better when he flipped the image. But the symmetry matters. And in fact, there's a very nice parallel, but perhaps one of the biggest achievements done in physics here at the Institute, which was the discovery, I would say 50 or more years later, that actually in elementary particle physics, a mirror image matters, and that in some sense nature is not mirror symmetric. T.D. Lee and Xian Yang, then very young, 30 and 34 years old, members here of the Institute, brought forth this idea. They got, basically the next year, it was verified in experiments, and they got one of the fastest Nobel Prizes ever. And in fact, there's this famous saying that Pauli actually in disbelief said that he couldn't believe God is a weak left-hander, that the world is not mirror symmetric. So it's a beautiful line in scientific research. I'm telling the story about how van 't Hoff came to his idea. Because when he became a professor at the University of Amsterdam, the title of his initial lecture was not about chemistry. It was about the power of imagination in science. And it was a response to one of the criticism he had when he launched his theory by one of the famous chemists at that time, who said that Dr. van 't Hoff, who was then at the veterinarian school, he had not done careful analysis, but he had mounted his horse Pegasus and flew directly up to Mount Olympus to basically say how the world is. So he made a big jump, so to say. And van 't Hoff was very, very angry about this. And so he wanted to give an answer. Interesting thing is, if you read the passage, the next paragraph is, Germany will do very bad if she cannot foster talents like van 't Hoff. But he apparently didn't read past the first paragraph because he was so upset. So his thesis is all about imagination. He does a very careful scientific approach to this. He takes 200 famous physicists and chemists and mathematicians from the last 300 years and analyzes them in three categories. Those without imagination, which he means like interest in general culture, and those with imagination. And then there's a third category with those with too much imagination. And that includes Ampere, Descartes, Leibniz, Newton, all very famous words. And of course, then he goes on to argue how important it is that we allow this free thinking in the scientific enterprise. And you can see many of these moments in crucial phases where, in some sense, science went through the hill. Max Planck, for instance, has this beautiful quote about the birth of quantum mechanics, that in some sense happened very much against his will. He was a very conservative person. He said it was an act of desperation. I was willing to make any offer to the principles in physics that I then held. And another lovely quote by Wolfgang Pauli. Here is actually a picture of him here at the Institute. He was a professor during the Second World War. He was celebrated his 45th birthday. He would actually earn the Nobel Prize a few months later. When Pauli first heard about quantum mechanics, and you know, in quantum mechanics, an electron can sometimes be a particle and can sometimes be a wave. And his friend Heisenberg, very young at that time, came up with that theory. He wrote to his friend Heisenberg, Heisenberg wrote to Pauli, and within 1 week, Pauli wrote back a postcard, and it said, I think I understand what's going on. If I look with my left eye, I see a particle. If I look with my right eye, I see a wave. If I open both eyes, I become crazy. And so it's a little bit like this, this picture, you know, you can see a young lady or an old lady, depending on your point of view, but it's very difficult to combine. Again, I think a major step, a major transition in our thinking. I want to go through a few of these other moments. In the 18th, 19th century, of course, there was a beautiful developed theory about the universe in terms of the movement of the stars and planets, classical mechanics being the basis of all of it. And then in the 19th century, there was a big question whether this beautiful clockwork that is the universe actually is stable. You know, can it happen that the planet Earth at some point get ejected and we find ourselves, say tomorrow morning, in intergalactic space? And so there was, in fact, a famous contest written by the king of Sweden to prove this theorem. And a proof was given by Henri Poincaré, at that time, and I think it's one of the great giants of mathematics. And he was a young mathematician, he put in his entry to the contest, and then he certainly realized he had made a mistake. And he wrote to the prize committee and said, I want to withdraw because I made a mistake. And the answer was, unfortunately, you already have won. And in fact, he had to use his prize money to pay for a reprint with the corrected version of the proof. But of course, this was not seen as a big failure in his career. It's seen as the birth of a new field, a field of what is colloquially known as chaos theory. Kind of the fact that small variations can have enormous impact. So he was really at that time taking a sharp transition in our thinking about mechanics. And he was actually involved in a second such thing, which is then we go back, or we go further a few years to beginning of the 20th century, when of course Albert Einstein came, and Albert Einstein gave many talks about the relativity of space and time. Poincaré gave the similar talks, and they never referred to each other. In fact, they only met once, and the time they met was on a famous meeting. It's the Solvay Congress in 1911. Last year we had the 100-year celebration of it, which was in some sense an interesting moment because it was the first real international meeting ever. And it was sponsored by a philanthropist. Solvay became very rich through his chemical factory, but he was really interested in the foundations of physics. At that time, people were discussing, can physics be saved? Because quantum mechanics was brewing, so to say, and there were lots of problems, but there were not yet a solution. And in the minutes of the meeting, there's a famous discussion between Poincaré and Einstein, I would say the old man and the young man, where Poincaré asked Einstein, on what mechanics is your theory based? So the new quantum mechanics. And Einstein gave a famous answer, saying, on no mechanics. And then Lorentz, the Dutch physicist who was chair, here he is, chair of the committee, summarized it, said that Einstein, you are beginning where we want to end. So again, a kind of a jump. The nice thing that after the meeting, Poincaré, Einstein writes back and says, well, these were a bunch of old men, they didn't understand. Only Lorentz he liked, but Poincaré was just a grumpy old man that didn't have a good interaction. Poincaré actually wrote a recommendation letter of Einstein saying this is a brilliant person who will go on to do great things. So you can decide who was the greatest personality, so to say, of the two. I'm also mentioning this event, and I want to come back to this kind of famous essay of Abraham Flexner, the founding father, so to say, of our institute, with the wonderful title, The Usefulness of Useless Knowledge, that at that time, so the 1911s, if you read about that, there was a lot of correspondence among the scientists complaining about the scientific climate. In fact, at that time, for instance, in the German university system, many of the leading chemists were complaining that these days, as they write, the general population and the government is only inspired by landscapes of factories and cornfields, and they look longingly back to the early 1800s, when still, life in academia was a paradise. So already at that time, I think it was felt by many of them that the freedom to think and freely, in some sense, was really disappearing. And in fact, you can really follow that path to the thinking of Flexner and the foundation of this institute. And of course, he made a beautiful point in this famous essay that free thought and the curiosity-driven research, as we now say it, can have tremendous impact in the real world. And he gives many examples. And I think we are always kind of mistaken, that we want to think in some sense of research either being good for knowledge per se, or it has some societal good or economic good. But we are thinking of these three things as kind of independent and orthogonal to each other, while they are, of course, much more integrated. And it's easy to prove this looking back in history. So, in fact, even if you take this quote perhaps a little bit out of context, I'm a bit afraid to quote this in front of a serious economist, but Adam Smith himself says that there were so-called philosophers or men of speculation are very important. They can see the power of the most distant and dissimilar objects. So the role of knowledge, I think, the creation of wealth and good was already there from the very beginning. And indeed, if you go back, for instance, to electricity, you could actually easily, I think, say that these days 100% of what industry is doing is based on electricity. So in less than 200 years, it completely transformed itself from a curiosity in the laboratory to everywhere. And if you look at quantum mechanics, for instance, which we're now kind of celebrating 100 years of, I would actually claim that like roughly 50% of all the industry, certainly the high-tech industry, is based on quantum mechanics. Often we are now down to the individual molecules and things are around. And it's very difficult to see these first beginnings. In fact, if you go back to the Solvay meeting in 1911, that year was a famous discovery. You see I'm highlighting some Dutch discoveries for you. It's my old roots. Actually of superconductivity, which was discovered by Heike Kamerlingh. So it's the property that the very cold materials, a current will go on and on at no cost. It was not discussed at the Solvay meeting. People didn't know how to think about it. Now we are 100 years later. We not only have trains that use that, but much more important, anything that you read about modern brain science is based on fMRI scanners, which can only work because of superconductive magnets. So it actually led to a discovery of a whole new realm of science. And in fact, you can even say that the discoveries in fundamental science themselves, like the discovery of the Higgs boson that we are living through, that is only possible because we can build these gigantic particle accelerators, which are based on very powerful superconducting magnets that keep the particles that zoom around with almost the speed of light somehow in track in these large kilometers-wide circles. So there's a very direct implication, but sometimes you have to be patient. In fact, interesting to see even in more recent times. So in 1939 in New York, there was the so-called World's Fair, which was about the world of tomorrow. And many people have commented, if you see what was highlighted then in 1939, many things were missing that in some sense very fast after that would completely alter our society. So both nuclear physics and computers weren't there. Actually, you would have taken train ride at that time down to the institute here. You would have seen the very first beginnings of both of them. And in fact, if you look at this is the floor plan of Foote Hall 10 years later, in some sense it's almost too much geopolitics crammed in one hole. You would have Einstein, von Neumann, Oppenheimer, the beginnings of the first programmable computer, of course all the aspects of nuclear arms and nuclear power, also the peace movement, it would all be there. But clearly absent in this World Fair. So I think this is some aspect I mentioned. I now want to take you to a few other aspects, kind of a few other borders that I'm sometimes upset with. One, I think, is actually the borders within science, within the knowledge field. I think often I feel that, we are, scientists and scholars are a little bit like a hyperactive butcher. Now we are kind of subdividing fields. And often there are more fields coming, but there are very few efforts that actually bring world together. I think one of what makes this place kind of very special is that we actually are forming or trying to form one community. And in fact, if you see many large institutions, they have a certain tendency to get very bureaucratic and sometimes very difficult to learn each other's language and actually get to know each other. And I think that's bad for many reasons. And one thing I want to just spend a few minutes, I think, which is kind of the modern paradox of knowledge, but is the fact that anything you learn about progress in science and humanities is by definition somebody digging further down in these very deep layers of knowledge. So that means that that information, that knowledge, is very far removed from you and from everybody. So to say, kind of scientists have to walk all the way up out of the mine shafts to bring this to you. But at the same time, because of all these new details, it's becoming much more relevant. So, in some sense, the world of knowledge is both very far away and it's very close by. And in some sense, literally in your breast pocket, or perhaps you have, medicines that are individually tailored, very high technical network technology that's influencing us. So we are, in some sense, the border between science and society becomes, I would say, kind of a fractal border. It's not quite clear where it is, and it's infiltrating parts of it, but it's often not visible. And I think this creates a lot of problems in the way we are dealing with this knowledge, and how we are, in some sense, able to connect ourselves to what's happening in laboratories, in the minds of scientists. And to make this even more complicated, this is happening in a world where actually information is freely flowing. Some people talk about the University of Google, or that people think of knowledge as the way you can get it in the digital world. It's not vetted, it's not weighted, it's everywhere. And one of my famous quotes in this context is actually coming from a wonderful theoretical physicist, unfortunately passed away much too soon, Sidney Coleman, who said, "The problem with the global village is all the global village idiots." And this makes it actually, in some sense, easy to become very pessimistic in how we can actually, as scientists, interact with society. For instance, how are we explaining and how we're communicating very complicated concepts? I use this slide not to give a little mini course about sustainable energy, but this is typically if you have a debate about an energy portfolio. This is what scientists come up with, very complicated portfolios. And you can, just to bring across these variants, just this from any distance look like a complicated graph. And how can you in some sense compress that in terms of language and choices that people can understand? And often I think these debates, these discussions are held in a way which is in some sense very hostile to scientific knowledge. And if you have to take these very complicated issues and you have a one-on-one, we actually are in some sense vicariously, I think, feeling all of that. That it's, no, this is in some sense a very unfortunate way to come to a conclusion. Often these kind of things can end in a draw, irrespective of the arguments, the scientific backing, the thoroughness of thought that is there on either side. And this is something I think that we see just becoming worse and worse and worse. And there are many examples of that. So one example, which actually is the example that Harold referred to, and that was kind of our own little adventure, was in climate change. And it's a very complicated world, of course, but in some sense, the famous example that people always talk, if they talk about the weather, is the butterfly. The butterfly who claps its wing in Brazil and generates a tornado in Texas. It's always a tornado in Texas. In fact, one of my colleagues said that we never talk about all these butterflies that prevented a tornado. And also remarked that often the speaker makes certain hand signals explaining this phenomena, which create a much worse tornado somewhere else, I think. But I think the butterfly effect I want to mention is the effect that small events can have on the public opinion. So this was the famous debate, and perhaps you know it was a mistake found, one of a few, in a 3,000-page report by the IPCC, the Intergovernmental Panel on Climate Change, about the melting of the Himalaya glaciers, where they said they would be gone in 2035. Well, the committee chaired by Harold analyzed this in great detail. The important thing is that that mistake didn't propagate to the main conclusions to the report, but it did propagate to the press, and it had a tremendous impact on public awareness of the issue. And in fact, as this headline in the poll said, that at that time there was like within a month, there was a 30% swing in public opinion, just because of this effect. And I think we see many of these. I just came back from a discussion in Japan about the fate of nuclear energy. And of course, there you see a similar impact, that public opinion can wildly vary. In fact, also policy can wildly vary. And as a scientist, you have a very difficult role to kind of play a certain role there. And of course, with global warming and climate change, we have went through this. It's clearly that the way the scientists are thinking about this and the politicians are thinking about it is very different. And in some sense, there are people out there, I think very brave, who in some sense want to bridge these two worlds. Well, the effort that we together went through, which was an analysis of this procedure, I think was one of only a small group of efforts I know, where people in some sense try to calm down these kind of stormy seas of public opinion and get this whole debate based on a good scientific basis. And I still very much love, I think it was The Economist who summarized this effort in 2 words, namely tough love. And I think that was the kind of thing that you need. We are very supportive of science as a whole, but we have to be and will be critical. I I'm telling this also because many of the issues, of course, that we are confronting are over the world. And the last thing I want to talk about is the borders between countries. And this is a map of the world, as you understand. It's interesting because it's a map where the size of each country is its actual size. And you see again how large Africa is and how small Greenland is. This is actually the map of the scientific world. I don't have the latest one. This is 2002. But you see the countries represented about their output, scientific output. And if you ever want to give a lecture on the needs of more scientific capacity in Africa, you can base it on this graph, because you see this gigantic continent basically melted away. Here you see Singapore. You know, there are some kind of highlights. Of course, the Netherlands is very conveniently in the middle. But clearly, our scientific resources are very unequally spread. By the way, as a new director, I did look in some sense where the present faculty were born. And if you distribute the institute faculty, you see that we actually are, in some sense, and I'm very proud of this, a good representation of that scientific world. We are truly here an international place. I'm sharing with you, if you again look at some of the great issues that the world is confronting, for instance, climate change, you see in some sense the places where the impact is largest are often not the places where the scientific knowledge is or where the measurements are. So there's a big contrast here that some of the issues that the world is confronting are not, in some sense, are not served well by the scientific infrastructure. So what are the solutions of this? Well, of course, my title, I borrowed a little bit from the famous report of Science, the Endless Frontier, that started in 1945, in some sense, the modern scientific revolution, the building of large infrastructure. And already in that report, Vannevar Bush, who is not a relative, I always have to say, said that, you know, there is a great responsibility here in what he called that small body of men and women who understand the fundamental laws of nature and are skilled in the techniques of scientific research. And I think there are indeed many kind of multipliers. For instance, if you think about physics, just to give you an idea of the number, if you do the number of basic physicists, scientists, jobs in technology, and the total population, see there are large factors in between. Often it's a small group that works on the very foundations. But then there's an enormous multiplier by bringing these thoughts and ideas up, in some sense, to jobs in technology, but in the end, I think, to the general populace. So I think there's a great challenge for us, I think, certainly working at the very bottom of this, sort of the deepest levels, to connect to this larger society. And how to do this? And perhaps that's the last thing I want to bring to you, which is something I've been very active in, and I feel very strongly about, is that it is possible to reach out. I did this myself in the Netherlands in a very modest way by, for instance, I have a website that small children can go to. They can do little tests. So I'm sometimes very proud when one of a parent comes up and says, well, you know, my children, if they have half an hour before dinner, they go to the website to do a little test. But I just mentioned this because there's one experiment there that I was thinking of doing it here, but I think I'm violating some fire codes if I do so. But you can go home and do it yourself. And the thing you do is you fill a balloon or a plastic bag with water, and you take a lighter or a candle. And of course what you do, you hold the candle below the balloon, and preferably do this above somebody's head or something, just to add a little bit more of the... And in fact, the nice thing is, of course, nothing happens. And I once did this experiment on television, and so I did this, and then, of course, the interviewer, they asked him, why are you doing this? And I said, what do you learn? Well, many things you can learn about properties of materials, and they say that the heat capacity of water is very large. It takes a lot of energy to boil a kettle of water, and if you have an empty kettle on the stove, it's there for 5 minutes with the fire on it, you don't dare to touch it. If it's filled with water, you do. And I was explaining a lot of things about physics. And then next morning, I got an email from one of my colleagues, a very respected physicist. And he said, well, I saw you on television, and I liked the experiment, but your answer was completely wrong. Oh, no, I said, this is this story about, properties of water material. That's not why you did the experiment. Why did I do the experiment? And why did I do it on top of, above somebody's head? He says, because the lesson that you could learn is that you can trust science. And I think that's a very true statement. I wish I had made the remark. So I think his point was that there are certain aspects of the way we acquire knowledge in the sciences, but also in the humanities and the social sciences, that in some sense are universal, that a young child can understand. It actually can experience. And it's a way to connect to the larger effort. So, of course, it takes many, many steps to go from a candle and a water balloon to, say, string theory or black holes, or the Higgs boson. But still, there's a continuous route, and I would say the principles on which this great building, this kind of great scientific edifice is built, these principles you can understand, you can get close to it, and you can experience it firsthand. And then you can really understand from the inside out, instead from the outside. So I think in that sense, I strongly feel that there is I want to end this talk on a positive note, that I do feel there are ways to reach out and to connect. And I think it's very important, and let me finish by, because I'm very much aware I'm speaking here to a group of friends in many ways. I think it's also part of the Institute, we feel very strongly that we can reach out to you, and we kind of feel your support in many ways. And I think this is in some sense a microcosm of what should happen out there in society as a whole. I think it's very important that we bring scientific efforts in close contact with people who are open to this. And so in that sense, it's for me a special, I think appropriate, not only an honor, but appropriate, that my first official talk here at the Institute was in front of you. Thank you very much. So I think, Harold, you insisted that we were self-organized enough that I could take questions. Right? So are there any questions, remarks, comments, criticism? Harold? So there's a microphone coming in.
I just wanted to ask, first of all, with respect to the water balloon.
Yes.
In your experience dealing with young children and access to some, can you characterize the children that are attracted to this? Are all children as only very special people who have very special qualities? Who is sort of accessing the website and running experiments and so on?
It's wide-ranging, and perhaps I want to give you one anecdote. I went to a class and actually gave a lecture about large numbers. In fact, I worked up to the question, how many molecules are there in a glass of water, which is a really big number. And when I entered the room, there was a little boy sitting in front of the class, and he was like with his back to the rest of the class. So I asked, what's wrong with this boy? He said, well, he doesn't understand things, he's very bad. And I felt it was a little wagon of the train that was decoupled. And then I started to do this, and I started by, of course, having the children to guess. And they had to be familiar with big numbers. And so I asked various kind of questions, and the little boy, he was like there saying 1 billion or something. It was right. So the first thing was kind of just by accident, but he was right all the time. And then we started to do experiments, and he was actually very good in this. So he was actually miserable in doing kind of arithmetic and spelling, but this actually he did very well. In fact, he did so well that after a few months, his father came to me and says, well, my son wants to go on a holiday trip with you, because then you can do these experiments all the day. So, and my feeling is that there are various kind of dimensions to, I think, to the sciences. And it's often like if you approach it in a certain way, it's like tilting. Often what I feel, a class gets tilted in a different way. And in some sense, the natural order gets shifted. Because there are certain qualities in children. For instance, some are more experimentally oriented. They're in some sense more adventurous. Others are more collaborative. And it depends very much on the style. Of course, there are always the group of children who know more about the Higgs boson than I do, basically, at 12-year-olds. And that's nice too. But I think actually often I feel one of the messages here too is that there are so many different ways in which you can approach knowledge. And I feel it's a very rich environment, and you see this reflected, I think, in academic life, because there's so many different styles and so many different interests. And so the amazing thing, so overall my thesis is that for everyone there is a certain direction. If you approach it, they will react to it. Yes. There's a microphone coming. So.
Thank you for a wonderful talk. It dawned on me that as a child we had an ambassador of science called Carl Sagan. So he would talk about, billions and billions and billions and all this. And yet it seems like in the last 20, 30 years, while you've been an ambassador of science in your home country, I'm not so sure we see that so much in the United States. And I was wondering if you had an explanation of why science in this really technical age that we have has played less public role.
Well, it's some kind of a paradox, and I think one of my questions I do have, certainly now about this country, because let's be honest about this, that if you, I say there's a lot of scientific effort across the globe, but if you really look where, in some sense, the best of the best go to, I think this country is still the predominant country by far. So it's extremely conducive to scientific research. Yet, on the other hand, there's a very strong anti-science thinking, and politics and many of the scientific discussions are extremely polarized. In fact, there are many, it's almost looked at, if you look at the countries that are well established scientifically, often they come also with a very intense debate. So I do feel actually that, and I don't have the solution to this, but I can see the problems. It's quite a challenge in some sense to speak out, and I think it's in some sense easier to say popularize science or bring parts of science to the attention of the greater public that in some sense are very remote. So it's in some sense easier to talk about string theory, about cosmology, about very speculative parts of brain science than actually to speak about the things which are in some sense much closer to our interest, because in some sense they get this kind of political dimension. And the only thing I know that this is not an effect that will go away soon. I think, and the only thing I feel is that it's up to also to the scientific community to find our way around. I think in some sense, I say both the atmosphere and the whole landscape, so to say, in which we are operating is changing very much. And I think the United States is in some sense ahead, perhaps, I would say, in other countries in these effects. And but it's clearly something, a phenomenon we see worldwide. So my own approach, I often say to young people that I think we should also approach not only science itself, of course, is a research effort, and we see it as a research project, but I think also outreach and building bridges between science and policy. Perhaps we should see it more as a research project, where we do trial and error and kind of work our way slowly, taking perhaps small steps, but in the right direction. And I guess some of that creativity that I mentioned that was so extremely successful and is so successful in making scientific breakthroughs, we need some of that, I think, also in this more public realm. Yes.
Now that you've found the boson,
Yes.
what are the things you're going to look for next? I know you're going to try and find out more about the boson, and I know you're going to look at a million different things, but maybe just 2 or 3 things that you could tell us that you're going to look for.
Well, I think, to be honest, what particle physicists are now looking, I feel they finally cracked open the safe, so to say. Right? So we were aware that there was a certain phenomena. We roughly knew at which energy scale it was sitting. So now we have seen that. Of course, we're all hoping. Well, first we have to we can now kind of enter that room, and we want to explore it. That is that we get now a period, say the next couple of years, of very detailed analysis of exactly what's going on there in that particular energy or length scale. Hopes are there, of course, that not only we find out precisely how the Higgs boson works, because now we only established there is an effect, we didn't see what the precise characteristics of the effect are, but there's also great expectation that together with the Higgs boson, other parts of the puzzle of physics are coming there, because we know from a very fundamental way that even with the Higgs boson, the standard model of elementary particle physics is not closed. It's not already, one of the candidates, of course, is the dark matter I mentioned, so part of this 96%. But also the internal consistency of that part of nature that we have now discovered is not there. So we basically we know that we need extra parts to make it a running machine. And the hope is that some of these extra parts in the form of new particles or perhaps new symmetries will be found at that scale. But we have to be patient because it means that we have to upgrade, and one will upgrade the machine. And then the coming years it will run with even higher energies and greater luminosity. And so I think in a couple of years we'll have answers to these questions. So in some sense it's a very exciting period. I mean, what I tell often to my students is now we have been waiting for 25 years for this. So you're extremely lucky to be active in this period, you know, the coming years. I think they're just very exciting. And one thing I should also say, because people don't get across that feeling, that this machine was planned 25 years ago. And it was planned 25 years ago, and I wish you think back about kind of the computers you were using 25 years ago. It was planned with the technology they would imagine was available in 2012. In fact, for all the parts of the machine, the projected technologies weren't there. They were just planning that science and technology would progress in 20, 25 years to be there. And not only all of these components one delivered, they're there, but the thing is also working. So I think that's absolutely, also from a technological engineering point of view, it's a tremendous effort. And we shouldn't forget that it's of course wonderful we have this particle, but there's also a collective effort of 10,000 people to build a machine that in some sense couldn't exist. It's pushing all the frontiers of any possible technology. There's a question here in front.
Thanks. It seems to be clear that this whole business of the kind of imagination you've been talking about and the advance of knowledge, the participants and major players in that historically tend to be younger, and as people get older, they don't seem to be as good at that game. I'm wondering what your thoughts are about that, and in particular, kind of in one sense, you can think about this as brain science, and your brain becomes less able to do these things with age, or you could think of it as being acculturated, having to do, and maybe it's a mix of the two, there's too much stuff cluttering you up, so, and you don't know what, you kind of don't know that what you're doing can't really be done until later on you know it probably can't be done. What are your thoughts?
Well, certainly, I mean, it's just a fact that if you look at the, and now I'm particularly talking about the theoretical work in mathematics and physics, often done at early age. And there's no disputing there. But there are two remarks. So first of all, I think it's right that you have this phenomenon, which is kind of amazing, I see, that you have very young people. They see this big building of science that we all are thinking is pretty much finished. And they say, well, there's something missing. They certainly see there is you can add a whole new wing to it or something. And certainly there's a certain freshness of, and perhaps also the fact that you're not intimidated by too much knowledge. And one of the wonderful effects, of course, in which science is progressing, that certainly our body of knowledge grows, but it also sometimes it compresses. So you have a big chunk of knowledge that in some sense, instead of having 20 suitcases, you can just compress it to something very small, put it in your backpack and move forward. But what this effect doesn't capture is that I think the scientific community is very much a collaboration of people of all kinds of styles and ages. Because apart from just people making this kind of very focused breakthroughs, you also have to have scientists who bring the world together and see the unifying themes. And often, if you describe science like this, you often recognize how, for instance, the great achievements in humanities are described. And often there, the arguments only at a much later stage in your career can you actually write the grand book compassing all of that knowledge. But I think that's also a caricature, because there are very brilliant young humanists who make efforts like that. So there's a kind of an overemphasis, I think. Of course, it's very romantic, and it's just seeing it happening, I would say, almost in front of your eyes, is amazing. That a young person can come up and, in some sense, without studying the full breadth of the literature, just makes the right move, semi-intuitively. And it's a great gift. I think that's why we, every year, if the new freshmen come, that everybody feels optimistic, because it might be an opportunity for a real breakthrough. But I think it's, if you be more honest and you see what the major achievements are in the full breadth of activities, you see that people at great age actually keep on producing and sometimes do things that people at a young age don't dare to do. Go back, all the back, yes.
Thank you. It was really fun. I really liked your fractals relation between society and science, but I was also very struck by the power of the political, which I don't know if that would be part of science or part of society in your Venn diagram, but even that moment where you see these incredibly well-funded inimical interests to something like the fact of weird weather or climate change, and Murdoch and all of the people who back that, sort of able to make that kind of change in public opinion because of very intense economic interests.
Yes.
Against what it would take to actually confront climate science. So I was wondering if you could talk a little about the less romantic sides of this.
Well, I think that, again, this is something that's sometimes depressing in the sense that, and we have to think in some sense also how to fund and how to organize science. So one thing which I find very interesting in looking at, for instance, the way climate science is organized, because that's organized as a network. So it's basically a voluntary collaboration of many people around the globe. The central budget of the IPCC, I think it was a few million. And when I first saw that, I think, well, I just misread. These must be billions. Because I was thinking, it's also based in Switzerland, I was thinking in terms of CERN, which, of course, is a centralized operation. And I think, for instance, also, if you look at the LHC and the whole operation in CERN, it also had to deal with a lot of public controversy. When it was about to switch on, there were rumors that a black hole would be formed that would eat up the whole world. And in fact, some of the people who wrote papers claiming this were now drafted in a committee to prove that it could not be done. But it was a serious effort. I think actually the public relations in Geneva, CERN has a large public relations office. They manage this. They were very open to this. I think when they came out last year with these neutrinos that went faster than light as something they misstep, and I think that was not such a good deal. So you see actually that there is some way to approach this. But clearly this is a very major organization that's centrally funded and is well structured. If you see other efforts, whether it's in the climate change or biodiversity, etc., it's much more fragile in many ways. And well, in some sense, the forces by which it interacts are quite massive. And as you say, the budgets are orders of magnitude larger. So I think this is also a lesson in some sense that, and I think this is something that the world is still struggling with. If we really want to be advised about global issues in a serious way, I think we should also seriously support these international organizations. And, but this is sometimes very difficult, very controversial. And if I have a bad day, I actually feel that it's on purpose. Some of these organizations are left weak, even organizationally weak, because it's in some sense that's to the advantage or something. And I think that's again something that the scientific community should address. I think there are issues where we can come together and we can organize ourselves and let the facts speak, so to say. But again, the forces, so to say, that are acting upon these efforts, they are tremendous. And you shouldn't be naive about this, I think, about how well organized they are sometimes.
Perhaps one more question.
So thank you for the talk. It was really wonderful. I just thought maybe you could comment on the kind of dual role that you mentioned that science has to take on, which is the role of both the skeptic and the role of giving us knowledge. Yes. and being sure about that knowledge, which seems to be, simultaneous. And it must be very difficult. I've thought about that just being here all these years and watching all the skeptics, yes. Who are questing for knowledge. At the same time, the public wants knowledge that's surefire and soundbite and easy to explain and simple. And I was just wondering if you might comment.
Well, I think I'm actually optimistic about that, because of course it seems almost like an impossibility. You have to steer the ship, so to say, between two cliffs. One is of being kind of very kind of fleeing away in the uncertainties in some sense, or not daring to make standards. And sometimes that is actually a very good strategy to attack science, what's called hyperscience. For instance, this happened very much when the whole debate about smoking was there, that companies would argue that you need more and more research to get to that point. On the other hand, I think you also shouldn't have false certainties. And I do feel that actually you should be able to communicate this, because life is full of situations where we have a certain amount of certainty and still we are acting upon this. So I think human beings are surrounded in a world which is not a mathematical world. We don't have perfect knowledge. And people can have insurances. They know what is a reasonable price to pay. So there is some understanding there. I think it's very important that these basic facts about how science works and how the uncertainty works are trained. I think that's something that you can learn. I think education plays an important role. But I also feel that it's not impossible for us. There are certain domains where we really are able to do this. And so I think it's to scientists also to, in some sense, train themselves to be very careful. And one thing I found interesting, at one point I taught a course, and with students we looked at what scientists would write and what they would actually say when they are interviewed, like in the news or on television. And they would tend to say things which in some sense are much too strongly worded compared to what they have written. Because I guess they felt, my message I have to come across, so I turn up the volume, so to say. So I think there are also lessons that you can teach students, young scientists, how to kind of behave in that environment. But I'm really convinced there is a middle course, and I think many of our institutions are convinced. For instance, national academies typically feel that they can play a role where they summarize knowledge and they bring it to whatever party is interested in that, and that there is a fair process by which not always by consensus, but there's a certain spread of opinions. And there are certain processes by which you can get to results. And I think that, in some sense, that's a responsibility of a scientist to walk this narrow but middle path. But I think it's still there. You can pass between the two cliffs.